Okay. Hello, I'm Ethan.
I'm Maxwell.
And I'm Stephen. In the past week, we have been reading about and implementing the variational quantum linear solver algorithm and the variational quantum eigensolver. First, let's talk about the variational methods, which are used by the algorithms. So what is a variational method? First off, variational methods are hybrid algorithms. This means that they are algorithms that combine two different methods, the quantum subroutine and a classical optimizer in our case, to solve some problem. Variational methods are also iterative, meaning that they use the previous results to get closer to the actual value. Lastly, these methods are much more resource efficient. Since variational methods do not use many qubits and quantum computers do not have many qubits, these types of algorithms are the most realistic option for near-term quantum computers. Now we can start talking about the variational quantum eigensolver. Given a Hamiltonian matrix, which is a specific type of matrix, using VQE allows us to find its smallest eigenvalue. There are many applications of VQE. For example, in chemistry, the smallest eigenvalue represents the ground state of a molecule, while in civil engineering, the eigenvalue of smallest magnitude represents the natural frequency of a system modeling a bridge.
So after implementing the variational quantum eigensolver, we tested it on 9 random 2x2 matrices and recorded the percent error from the actual answer. We did this on an ideal simulation, which simulates how a perfect quantum computer might operate, and a noisy simulation, which takes into account the fact that current quantum computers will deviate from expected results. The ideal simulation performed very well, consistently getting within 0.2% error. The noisy simulation in comparison was much worse. However, considering that this is something that can be run on quantum computers we have access to today, a 4% error is still pretty good.
Here are the results of our practicality assessment. So the main things to look at is qubits and depth. Qubits is how a quantum computer stores information. It stores it as a superposition of 1 and 0. It's important to keep track of how many qubits a quantum computer uses because quantum computers don't have access to many qubits. Depth is how many gates are used. Each of the boxes with letters represents a gate and it changes the qubits value. It's important to keep track of depth because the bigger it is, the more error prone the algorithm is. And in terms of scaling, the main thing to take away is that you could give it a big matrix and you'd still use very few qubits.
Finally, we can look at the variational quantum linear solver. VQLS uses VQE to solve linear systems of equations using less qubits than similar algorithms. What VQLS does is that it makes a guess of the parameters that form the quantum state and then calculates the value of the cost function to see how close that initial guess was. One such application of VQLS would be solving partial differential equations.
Again, after implementing this algorithm, we tested it on 10 random systems of 2 equations and 2 unknowns. This time we recorded the cross product, which is a number between 0 and 1 where a lower number represents that the algorithm got an answer closer to the actual value. For observations, the ideal simulation consistently performed pretty well. There were certain test cases that proved to be difficult for both simulations, but in general, it remains within this 0 to 0.1 range. The noisy simulation in comparison fluctuated a lot more, going up to 0.4 at times. However, again, since this is something that we can run on a quantum computer we have access to today, that is still pretty good. Next, for the practicality assessment, the circuit is, again, pretty small. It uses 2 qubits and has a depth of 6 gates, which means that it's not going to use a lot of resources and it's going to run pretty fast. However, it's important to note that while the circuit itself is quite small, this circuit has to be run 1,200 times, and each time 4,096 measurements are taken. So the algorithm itself is relatively slow.
And we ran into a few challenges during this project, one of them being the lack of resources on the VQLS. The paper for the VQLS algorithm came out roughly 2 years ago, and so there was really only one tutorial for it. And if there was something we didn't understand on it, we basically just had to read it over and over again until we did understand it. So that took a long time to do. On top of that, the algorithm required lots of complicated math formulas, as you see in these pictures here. That also took a long time to understand. And with the algorithm being so complicated, we were only able to implement the algorithm with 2 qubits, and that meant it could only take a 2 by 2 matrix. And here are the resources, and thank you for listening.